Rosmarino.
Alexander Rosmarino, and his project name is Stellar Rejuvenation via Spin-Up. Take it away whenever you're ready.
All right, thank you. Good afternoon. Last presentation of the day, so let's go out with a bang and talk about stars. So, whoops.
Oh no, is it gonna give us issues?
There we go. Okay, so a little bit about me. My name is Alexander Rosmarino. I'm a senior here at Clarkson University in aerospace engineering. And for the past 8 months or so, I've been doing astrophysics research with Dr. Roulston here. He's an assistant professor in physics and the principal investigator for the spin me right round research that I'm going to be talking about. So back to my title slide. Spin me right round, measuring accretion, spin up, and binary main sequence carbon stars using X-ray and UV observations, which is a mouthful. But what does that actually mean? And to understand that, I'm going to break it down piece by piece, and I'm also going to use this physical model here to help understand it. So first, binary main sequence. Binary just means that we're going to have these two stars that are orbiting each other. And in our case, one of these stars is going to be more massive than the other, which will become important. And then main sequence just means that both of these stars are going to be fusing hydrogen in their core. Now, if we talk a little bit more about that, what that means. So during stellar fusion, we're going to be fusing hydrogen into helium. And so now, in that star that was more massive, that's going to happen quicker because it has more things that it can burn. And the byproduct is that we're going to start making this helium core, and we're going to start slowly running out of hydrogen that we can burn. And eventually, after a long time, we're going to have no hydrogen left, and we're going to have just this helium core. And that's going to cause the star to become very unstable and move to its next phase of its life, which we call the AGB, or asymptotic giant branch. And during this phase, we're now going to convert that helium into carbon, and we're going to start burning a little bit of hydrogen too. And what this is going to do is cause the star to become massive. And this star that was, one similar size is going to become this giant red star that grows over 200 times its original radius. And it's really hard to perceive how much and how big this star is. So for reference, when this happens to our own star, it will grow big enough to envelop Earth within its radius. So they're going to be absolutely massive. And so while this is happening, while the star is really big, we're going to experience binary mass transfer, where this bigger star is going to start passing on some of its material to our smaller star. And it's going to begin accreting it, and it's going to start taking on some of these characteristics. And the material that it's going to be passing is going to contain a lot of hydrogen, helium, and especially carbon. And that carbon is important because that's what's going to go on to supply our carbon star. So if we look at that, this star, which has now gained a lot of material from this star, we're going to call a carbon star. And we know it has that carbon because when we look at it, we can see these distinct carbon bands. But also, as it gained all that material, the material comes with angular momentum, and that's going to cause this star to spin up. And the faster stars spin, the more activity they're undergoing, and the more that's going to happen. And so this has a sort of rejuvenation effect where this star should be getting older, but now it appears much younger because it was just spun up. And so if we go back to our red giant, after this process has happened, our red giant is going to go, and it's going to eject this giant core because it was unstable, and we're going to be left with just the tiny core of this star that was inside of it. And now the star that was once big enough to swallow Earth is just going to be the size of it. And so we're left with this tiny white dwarf, and it's going to no longer undergo fusion because it doesn't have the mass, which means it's going to start cooling for billions of years. And between its small size and no longer producing heat, it's going to become extremely hard to detect. So now, if we go and we look at the system that we have and what we see today, we're going to see this really hot but hard to detect white dwarf, and we're going to see this bigger, younger, rejuvenated carbon star. This is the process that we're talking about. This is the accretion spin-up in this binary main sequence. But my research looks at measuring that. So how are we going to do that? Well, the answer to that is understanding light. Now, there's two very important things about light that we have to understand. And the first is that light is both a particle, called a photon, and a wave. And the amount of energy that that photon delivers is proportional to the wavelength that it travels on. Or the other way you can think about this is the wavelength of light we see corresponds to some energy. And the final piece of that puzzle is going to be understanding that temperature is just energy. When you feel heat, you're really just feeling the movement of molecules in whatever you're touching, that you're feeling their energy. So if we put this together, what I'm saying is, if we know the wavelength, we can find the temperature. And that seems kind of crazy, but we already intuitively know this. Think about your stove at home. When it's not on, it's cold and it's black and you can't really see anything, but as it heats up, it starts to become red hot. That red hot that we're seeing is the increase in energy, decreasing the wavelength, and it moves from the infrared and it starts to enter this red region of light. And so we already intuitively know this, and I'm just going to apply this back to our star. So to do that to our star, we're going to create what's called an energy distribution. On our x-axis, we're going to plot the wavelength of photons that we receive from the star, and on our y-axis, we're going to plot the energy that we receive. Now this star has been in the sky for billions of years, so all these telescopes have already seen this. So we can go and we can try to pull public data that's already available from the star, and we get something that looks a little bit like this. Now immediately you can start to see a trend, and you start to see this curve here. What we can do is try to fit a model to that using black-body equations, and if we can find out what this wavelength is, we can figure out what the temperature of this star here that we're looking at. So when we do that, this is what we find. And we find that our star has a temperature of around 3,500 degrees Kelvin, and it has a radius of 0.3 solar radii. But if you look here, a little bit of this data doesn't really fit. It kind of seems to break this downward trend that we had going. And we can't forget, though, that this is a binary system. So this white dwarf, even though we can't see it, should also have an energy curve. So where is that, and how do we find that? And to answer that question, we have to go to use our first spacecraft, which is going to be the Hubble Space Telescope. Now Hubble is really cool because it has the ability to observe in the UV. And if we go back to our light, that is lower wavelength, so it'll give us these points on the left side of our energy distribution. And so we went and we asked Hubble for 2 observations of our star. And Hubble got back to us and it said, of course I can do that. Here are the observations. And so these are the observations that it gave us, and these are the stars that we're looking at. And so this will give us 2 points. One in our near UV, which is right here, and then one in our far UV, which is here, and it's a little bit harder to detect as we get to that higher energy. And so with this, we can try to fit a model to our white dwarf. And so if we go back and we now plot those 2 points that we calculated, we can see we gain 1 point here and another point down here. And so we can see that we get that similar trend that we originally got with our first star. And so if we try to fit a model to the white dwarf, we're going to have to change a little bit, because now we have to assume initial mass and radius, since this white dwarf is only the star's core. So we're going to have to use a little bit different, but we can use the general process and we get this. And we find that our white dwarf temperature is around 8,400 Kelvin. And so now we can see that all this data fits really well, except this isn't actually what we would see. Because when we look at the star, we're going to see something that combines the two. So now, if we look at the combined curve, we can see, well, now we're not actually seeing our data. So what's going on there? And this is just improving our model, so we can start to include an atmospheric model that takes into account interactions with the star's atmosphere and how we would see that. And once we add that, you can see, and this line is very hard to see on this TV, but there's a line here within our combined curve that plots all these points, and we can see that these all line up very well. And so with this, we can find that this system, or this white dwarf, has been cooling for 650 million years. It's been 650 million years since this star transferred all of this carbon-rich material to our second star. And that's really important to know. And the second thing is that we can now say that our star system is 3 to 6 billion years old, and we can put an actual age on everything that's happening. Now what we want to know is how much did this star actually spin up when it gained that material? And to understand that part, we're going to have to go use our second space telescope, which is Chandra. And Chandra can see in the X-ray, which if we go back again, is even higher energy than our UV. Except stars don't really output that many photons with that much energy. And so what Chandra is actually seeing is the X-rays that are emitted from the upper atmosphere of the star, the corona, where the star will become more active from the spin up. And so because they're more rare, when we get data from Chandra, we're only looking at the individual photons. Each of these is individual photons. And so a star may only be a couple of these. This is only 25 combined photons from the star. And because of that, we're going to ask Chandra for 3 observations to try to make sure we can see something. And so Chandra gets back to us and it says, of course I can do that. Here you go, here's your data. And we got nothing. And so we didn't really detect a star. Maybe that's our star right there, but it's hard to tell because we don't see a lot. And so now, why are we not seeing this detection of X-rays? We thought they were going to be here, and they're not. And we can't really measure as much as we wanted to the spin up. So what can we learn from this? And it's important because no data is still data, and this can still be very useful. And this is where we get to our current day and our current work. And we're trying to answer two questions. One, why were no X-rays detected? And two, what can I do with the results that I do have?
So 10 minutes, we can go for 10 minutes.
And so, first, why were no X-rays detected? Maybe the mass transfer spins up less than we originally thought, or maybe because it's been 650 million years, the star has spun down. We don't know. We're trying to figure that out. What can we do? Well, we know what Chandra can detect, and we know what it didn't see, so we can put an upper bound on what it should have seen, which can still help us curate our data, and we can also discuss our results. We know we should have seen them, we didn't. Why is this shocking to us? So, thank you.
Any questions for our dear friend Alexander?
So, all right, I'm gonna ask this. What were you trying to do with this work? I'm not clear, I'm not clear what the motivation was. Like, are you trying to find these things? Are you trying to come up with a technique for measuring the stuff that's in there? Like, what were you trying to do?
So that's a good question. So we know that this exists, and if you remember Lucas, who's my colleague, he founded a thing that can find these systems. So now we're looking at these more in depth. And what we're trying to find out is when we pass mass from our first star to our second star, how much does that spin up and how much does that change the star? But if you notice, and the big point of the data that we received is that we didn't receive data. And so we really expected this star should be spun up. We've seen it has everything else of this process is there. Why didn't it spin up? And so this is the part we're trying to measure, but we didn't get data, so this part has taken longer and required different techniques.
So if you go back to like the data you got from the other two telescopes gave you essentially a temperature and a radius, right?
Yeah.
A size and a temperature.
Yep.
Like, what were you hoping so the spin up, if the thing was spinning at a different speed, would these plots be different, or?
Like they could. This isn't necessarily related to the spin-up speed. This is more creating the system and understanding what we're working with, understanding the mass of the two stars, understanding their temperature and how they've interacted with each other. And if we understand that interaction, we can better understand, how this mass transfer happened, right? If we know the radius, if we know the mass, we better understand the system that these two stars are living in.
And how would the UV measurements tell you what the spin up is?
So the UV measurements aren't to tell us what the spin up is. The UV measurements are to help us figure out what this white dwarf is. Because without the UV measurements, we have no idea what its temperature could be, what its mass, how long. And the most important thing about plotting UV data is figuring out how long the white dwarf has been cooling, how long it's been since this process first started. And so with the UV data, we can put a time scale on that.
Awesome. Oh, Min. This is a clarifying question, but could you explain what spin up means?
Yeah, so spin up really is just that. It's like, we have something coming in and it's going to orbit this star. And so this star is going to begin to rotate faster on its axis. And when that happens, there's a lot of forces. You have your centrifugal force and things like that are going to cause this star to change its behavior. And when it spins faster, it's going to emit more photons. It's going to look younger. It's going to be more active, if that makes sense. And so we're trying to measure how this star should be really old, but it kind of appears younger. How much did this process rejuvenate it?
Oh, okay. So then does the second star absorb the energy of the first star?
Yeah, in a sense. It doesn't absorb all of it, and it can't fuse the carbon that it has received, but that angular momentum that comes with it has spun the star up and given it more energy.
Oh, okay. Thank you. Awesome. Alexander, don't forget to attend the pitch off and the student awards ceremony at 2:30 and 3:30.